Okay, very honored to be here. Glad I was invited. My name is David Kaplan. You can, if you'd like to talk to me and you don't find me around, you can send me an email. I get several emails a day, starting with Einstein is wrong. Let me show you my theory. So don't start your emails that way because I don't read those, but everything else is fine. So I'm going to be lecturing about effective field theory. This is a tool that I've used in a large fraction of my papers. And so what I'm hoping to do is not just show you how effective field theory has been used in some standard well-known theories like chiral perturbation theory and so on, but to teach you many different ways that effective field theory has been used so that you can consider it a tool in your toolbox. So when you get to a problem that you want to solve, you could say, well, maybe I could use this to solve my problem and invent your own effective field theory. So first question is, I should mention my background. I was trained in particle physics. I now work at the Institute for Nuclear Theory, and I've also worked on some low energy few body nuclear physics. But generally, when asked what I do, it's applications of quantum field theory, wherever I can find them. So what is effective field theory? You'll see this acronym often. That means effective field theory. So the big question is, what is it? And probably the best definition is lying about short distance physics and getting away with it. Sorry, what? Yeah, lying and getting away with it. In a way that, as Daniel says, is very well organized so that you can have a hierarchy of lies that allow you to approximate reality at low energy. And the question is then, why do you do this? And one is that it pays well. You can win the Nobel Prize if you come up with the right effective field theory, such as the Standard Model, which we know is not a complete theory of everything because it's missing gravity, it's missing dark matter, it's missing neutrino masses. So it's an effective field theory that won a Nobel Prize. And in general, it's a tool that just allows us to solve hard problems much more easily. And these may be problems where you're at low energy and you don't know what the high energy theory is and you're trying to grope your way up to figure out what the more fundamental theory is. Or maybe a case where you have a theory like the Standard Model and you want to study some low energy implications of it, and you don't need all of the machinery of the Standard Model to get the low energy physics. So effective field theories allow you to simplify and do a top-down approach. So of course, if this is what effective field theory is, you might ask, what is quantum field theory? Well, the answer to that is it's equal to effective field theory. All quantum field theories are basically effective field theories, and that's the lesson that Wilson taught the world. Wilson completely transformed how we understand quantum field theory. It used to be that you write down a quantum field theory and you classify things as renormalizable quantum field theories, which are good, and non-renormal ones, which were bad, such as Fermi's theory of the weak interactions. But Fermi's theory of the weak interactions is very useful, so it was useful but bad. But Wilson pointed out that all these quantum field theories have infinities, and he had a very practical approach, which was he wanted to put quantum field theories on a computer. And you can't just sort of wave your hands at infinities on a computer. Computers can't deal with the infinities. So he had to come up with a very precise way of defining a quantum field theory on a computer, which meant a very precise way of dealing with these divergences that appear everywhere. And in doing so, he came up with the view that, in fact, the interactions in quantum field theory that were considered bad, the ones which were not renormalizable, he called irrelevant interactions. They actually had very small effect at low energy, like the weak interactions. While the things that people, and they're very healthy, It's very easy to deal with those on a computer. But the things that were bad were the ones that people really liked, which were the super renormalizable interactions, like phi cubed interactions or mass terms. Because there what you find is when you put it on a computer, you have to really fine tune your parameters up in your computer in order to get the right low energy physics. And so the whole view of there being a fine tuning problem for the Higgs and so on is a reversal of the old idea that there's nothing better than a scalar field with a mass. And maybe a 5/4 coupling. Now the mass is very problematic, while Fermi's theory is not. So his initial impetus to put a quantum field theory on a computer led to this complete change in understanding of infinities and led to this idea of effective field theory, which was then developed by many people, but the big name probably would be Weinberg, who developed the chiral perturbation theory and many, many other applications. There are just so many times when he was ahead of his cohort. He said, for example, what higher dimensional operators can I add to the standard model? And he immediately came up with Majorana neutrino masses, which are naturally light and things like that. So he's one of the big names in quantum and effective field theory. Now, one thing that always confused me when I was a student was why is it that when you take graduate quantum mechanics, it looks completely different than when you take quantum field theory. They're supposed to be the same thing, you just added relativity, but everything about it looks different. And there's several reasons, but for example, in quantum mechanics, you solve two-body problems, and you can solve some really complicated two-body problems exactly. While in a relativistic theory, there's no such thing as a two-body problem, because if you put enough energy into the system, you produce particles and antiparticles. So it's a many-body problem, and there are not many many-body problems that are exactly soluble. That's one difference. But the really big difference is that for a relativistic quantum field theory, you want to write down local Lorentz invariant interactions. And so the way you do it is with, if you draw Feynman diagrams, you have pictures of interactions at points. Which, if you took the non-relativistic limit of, say, for fermion interaction, that looks like a delta function potential in quantum mechanics. Now, we all learned delta function potentials in quantum mechanics, but if you look back, you say, oh yeah, we only learned it in one dimension, They always teach us the one dimension, let me say 1 + 1 dimension, delta function, where you have like a little attractive delta function here and you get a bound state on it and so on. That's one of the first problems you solve. But they never talk about delta functions in 2 or 3 dimensions. And there's a reason for that, which is that they're too singular to solve the Schrodinger equation. So they're considered bad. So you don't talk about them. In quantum field theory, you have to talk about them. And then what was considered bad in quantum mechanics now becomes part of everyday life. So for example, if you try to do a delta function 3 + 1, you'll find there's no ground state. You'll find that because if you think of a square well that gets deeper and deeper as you make it narrower and narrower, the depth would have to go like 1 over the distance cubed, the size cubed. So if I take this to be with delta, then if I wanted this to be a potential integrated to 1 the way a Dirac delta function does, I'd have to make this like 1 over 4π/3 delta cubed in depth. But you can see that a square well whose depth goes like 1 over delta cubed gets negative faster than the kinetic energy of a wave. So here the del squared over 2m term goes like 1 over delta squared. And so you have a 1 over delta squared repulsive kinetic interaction and a 1 over delta cubed attractive potential interaction. And as delta goes to 0, you find negative infinite energy. So the delta function in 3 dimensions is a sick thing. So you don't talk about it. But in quantum field theory, we talk about it all the time. And when we put this interaction, we do get infinities, just like you'd get in the quantum mechanics, but we deal with it, we renormalize. So you could have done that also in the quantum mechanics class, and that's what I'm going to talk about. And it helps understand some of the features of effective field theories. And that's really the biggest difference that makes quantum field theory look so different than quantum mechanics. So where is effective field theory useful? It's useful almost everywhere, but what EFT cannot do, one is a theory of everything. You want a theory of everything? You don't go to effective field theory. Go to string theory or something, you know. But the other thing is systems without a hierarchy of length scales. So for example, maybe turbulence, not an expert in turbulence, but I know there are cascades of length scales there. Or if you wanted to really discuss QCD in the resonance regime, where there's just lots of broad bumps that overlap with each other and there's no big distinction in energy scales, that's a tough place to use effective field theory. So let me start off with, I'm going to work in D equals capital D plus 1 dimensions, and we're going to start with D equals 1. And let's look at a square well. Very simple physics. I'm going to take this to be with delta, and depth is going to be alpha squared over 2m delta, where m is the mass of the particle experiencing this potential. Alpha is dimensionless. And I'll call delta is my UV scale. It's the scale at which the potential has some structure to it. And I will call 1 over delta be lambda, which is the UV cutoff. So if you do the solve the Schrodinger equation for this, you'll find there's a reflection coefficient, which is 1 minus the transmission coefficient, and it is equal to 4 kappa squared k squared over k squared minus kappa squared squared times 1 over sine squared kappa delta plus 1 inverse, where kappa, so I've got a wave coming in with momentum k, and kappa is square root of k squared plus alpha squared over delta squared. So that's the reflection coefficient. And if I expand for small delta, all k times delta, so low momentum, this is about equal to 1 minus 4 over alpha squared sine squared alpha times delta squared k squared plus order delta fourth k fourth. And so one thing that you immediately see that as k goes to 0, r goes to 1. Complete reflection. So this is a huge effect, no matter how weak. In particular, what I mean by this is that delta k is much less than alpha sine alpha. So as long as alpha is not 0, there's always a low enough k where r goes to 1. So we call this a relevant interaction, to use Wilson's terminology. It is relevant at low energy or low momentum. Becomes more and more important. Now, the essence of effective field theory is that I can get this exact same result from a whole family of potentials. I don't need to use that potential. And in fact, one thing you can obviously see is that if I change delta and change alpha, such that delta squared over alpha squared sine squared alpha stays constant, I'll get the exact same behavior at low k. I'll get the first two terms. I'll get 1 minus this. The order k to the fourth term will be different. So there's a whole family of delta functions that will give me the same behavior at low k, where I can take this thing narrower and narrower and change the depth at the same time. And in particular, I can mock this up with a delta function. So with the delta function, what I do is I take v of x is equal to minus g over 2m delta times a Dirac delta function at x. So I'm going to define my potential to be that. And you can compute the reflection coefficient for this one. And you find that it is equal to 1 plus 4k squared delta squared over g squared inverse, which is 1 minus, if I expand for small k, 1 minus 4k squared delta squared over g squared, plus order k fourth delta fourth. So again, r goes to 1 at low k. And if I take g defined to be alpha sine alpha, which is my matching condition. So what I've done is I've said, I tell an experimentalist, go do an experiment at low k and calculate the first deviation of the reflection coefficient from 1. They measured the k squared dependent of the reflection coefficient in the true potential, which is the square well, and then I find a g. From that, I can determine what. This is the true potential. They measure this term in the scattering. I can then set g to match this experimentally determined number. And now I have a theory with a delta function that gives me the same behavior at low momentum for r. So this is called a matching condition, where I took the coupling of my incorrect lying potential, which gets the UV physics wrong, but gets the IR physics right, and this is the matching condition. And as I said, in fact, there's a whole family of, if you don't want to put a delta function on your computer because it's difficult, you could say, well, in fact, I could think of this as being the endpoint of a whole family of delta functions where I change the width and make it deeper, keeping this combination fixed. And in that limit, that's what the delta function is, but I could just take delta b very, very small, but not 0, and approach the delta function that way. And that is an example of a regulator. I'm regulating the delta function by smearing it out, by calling it a very narrow but deep square well. So that's another concept we come across all the time in quantum field theory, and you can see the same thing in quantum mechanics. Now, suppose you wanted to go to higher order, what would you do? Well, there's no magic here. There's no way that you're going to get the exact same R from a delta function as you do from a square well. You can see it's a much simpler formula for the reflection coefficient than this thing, which depends on K in a very complicated way. But so there's no free lunch here. If you want to go to the next order in K to the fourth, you're going to have to add a new coupling constant and a second coupling constant to your potential. And so a way you could do that is you could have a G prime over 2m delta upstairs times derivative x squared delta of x. And you could now try to do the same thing and fit this, but you're going to run into a problem, which is that this is too singular to solve in one dimension. The delta function is not too singular, but this one is. So rather than focus on this, I'm going to go to a three-dimensional problem where you have a similar problem where the potential we want to use is too singular, and approach the issue of renormalization in the 3D problem instead. But in principle, you could use this with renormalization to fit the order k fourth term. And so on, and do higher and higher derivative operators, which still are point-like, and go to higher order in determining your R. Now, if you want to put this on a computer, what you might say, well, just like this could be treated as a sequence of potentials that get narrower and deeper, this might look like you could turn this into a potential that has some structure, something like that, which has an extra degree of freedom here inside. And you could take some limit of this as this gets narrower and deeper and model this thing using something like that. So, or maybe a better one to do is something like, yeah, well, that was good. But I don't want to get into that. That's sort of messy. Let's go to d equals 3. This will be a similar discussion, but then we're going to use some of the results from the 3D case to start talking about effective field theory for nucleon scattering. So it'll be a real world application. So a quick review. Of scattering in 3D. We have psi goes to e to the I k z plus f of theta over r e to the I k r. So this is our plane wave that was coming into the scattering center. And it's moving this way. It keeps going through, but you also get then this beta-dependent scattering that goes outward in a spherical wave. Then your cross-section, differential cross-section is just equal to f of theta squared, absolute value squared. And this all go back. Take the long hike to this end of the room and continue over here. So then, question, yeah. I'm sorry, what's the first part? If what?
Let's say we have some k cube delta cube term in the evil physics, then can that operator also capture that term, or
No, I was assuming that it was even in k. Yeah, if you have something that violates k to minus k symmetry, then you'll have to put in operators that violate the symmetry. Yeah, well, so in general, the rule is the following, and this is what Weinberg called a Folk theorem, which is a funny combination of meaning something that's very loose with something very precise, which is that if your effective theory has all local operators consistent with the symmetries of the theory you're trying to represent, then you'll be able to reproduce the S matrix. Yes, it also has to be a unitary theory, so the Lagrangian has to be real, for example. But it's not something that has been proven by mathematicians. It's a folk theorem. Everybody believes it to be true. Okay. So in the case where you had a k cubed part to the reflection coefficient, that meant that you must have broken the reflection symmetry that takes k to minus k. And once you've broken that symmetry, you have to include things that are odd and like d by dx of delta of x. Good question. So I should have prefaced my lecture that I'm also extraordinarily hard of hearing. You have to turn that on. Maybe, I'll try.
Okay, so when you match the theory, I mean, in the left-hand side is the only one coupling G, and the right-hand side is alpha sin alpha. It contains all the power of alpha. So what is going on there?
Yeah, so this is not the Born approximation where I'm doing a Taylor series in alpha. This is an approximation in powers of k. I don't know if this is addressing your question or not.
No, I mean that the right-hand side contains all power of couplings, right? Is dimensionless. Alpha is dimensionless number couplings, and it contains all power of couplings. And left-hand side is only G, one power. So when you match these, I mean, it means you consider all the interactions, all power of interactions in the first case, and that match to.
Can you help me with my hearing?
We're matching only the first term. Term by term, you're matching. Every time you expand in k square.
Yeah.
When you go to k4, then you write an additional term in dx.
Okay, okay.
Yeah, there's a one-to-one correspondence between the operators in your effective theory and the momentum expansion of your physics.
Okay.
And figuring out how to order those is going to be a key part of the effective field theory, which ones to include and which ones don't. I mean, how do I know that the derivative squared comes in before the derivative to the fourth term? What about that? It's called a power counting scheme.
But both results are non-perturbative, right? So as you said, right, the result is to all orders in alpha here, and G appears in the denominator for R, right? So,
yeah.
So both the result in both.
Yeah, both are solved non-perturbatively in the coupling constant. It's a completely different expansion than the Born expansion.
Thank you.
Okay, so let's talk about L equals 0, S wave. In this case, we can replace e to the ikz, which is equal to e to the ikr cos theta. For an S wave, we can replace it by its spatial average. So it's 1 over 4 pi integral d phi integral d cos theta minus 1 to 1, 0 to 2 pi of e to the ikr cos theta, which is equal to the spherical Bessel function J0 of kr. Where L equals 0 appears there as J0. So J0 of Z has a nice relationship to trigonometric functions, and it comes along with an irregular partner N0 of Z, or sometimes called Y0 of Z, which is equal to minus cos Z over Z. This one's singular at the origin. So we can write our psi is equal to J0, so this is L equals 0, J0 of kr plus, and then for, we have f over r e to the ikr. There's no theta dependence for the L equals 0 wave. And we can rewrite this e to the ikr over r in terms of the Bessel function. So we can rewrite this as J0 of kr plus k times f times I J0 of kr minus N0 of kr, which just, you plug in these functions here and you'll see that this is exactly equal to that. And then that whole thing can be written as an overall constant times cosine delta of J0 of KR minus sine delta of N0 of KR, where I've replaced F by this delta, which is the phase shift, and the relationship is between these two. So this is definition, and the relationship then is that F is equal to 1 over K cotangent delta minus IK. So, and then your scattering matrix is e to the 2I delta, which is 1 plus 2 IKF. And then this quantity here is very interesting because for a purely short distance potential, namely not a power law, it's something that's at least exponentially localized. You find that K cotangent delta is analytic K squared out to K on the order of lambda, which is the scale of the potential. And this was proved originally by Beta, I believe, and then a highbrow proof by Schwinger. And that means that you can expand K cotangent delta in what's called the effective range expansion. And there are higher order terms. And this is, A is called the scattering length. R naught is called the effective range. And typically, this scales like 1 over lambda, but this could be anything. We'll see that a little bit more clearly. Yeah. The scale, what I mean by the scale of the potential? Yeah, so what I mean is that when I say that the potential is purely short distance, what I mean is that you've got some potential and it is confined to a distance 1 over lambda. So if you're talking about a Yukawa potential, lambda might be the mass that gives you the exponential fall off, for example. It's not a hard and fast definition, but it's a scale that's order 1 times the support for the potential, where the potential is non-zero. Now, we can treat quantum mechanical scattering in a language similar to what we use for quantum field theory, namely with Feynman diagrams. And that's very useful because of we're going to have to deal with renormalization, and there's a huge apparatus for doing that in quantum field theory, which is not so familiar in quantum mechanical language. So it's nice to rephrase the scattering in this language. And the path is, I guess, strictly speaking, through the Lippmann-Schwinger equation, which turns the Schrodinger equation into an integral equation. But what it is you write down your Hamiltonian, or you write down your Lagrangian as psi dagger del 1 squared over 2m, I dt plus del 1 squared over, or del squared over 2m. I'm using a capital M there, psi, plus psi dagger psi at R1, psi dagger psi at R2, V of R1 minus R2. And you, then to get the action, you'll integrate this over space and time. And this just says you have some particle density at R1, some particle density at R2, and the potential between them. And then the scattering, so in quantum mechanics, we often get rid of the center of mass motion and pretend that two-body scattering really looks like one-body scattering in a potential. So a square well potential really means that two particles don't feel each other until they get within a certain distance, and then they feel each other, and then they go off and they don't feel each other again. So this is the radius of the potential is really the interparticle distance that we're talking about. So that's what appears here, how close together the two particles are. And then we can talk about scattering. We can compute a Feynman amplitude, which looks like this. I won't draw the arrows anymore. Where this propagator is 1 I over E minus P squared over, I've been using K squared over 2 big M plus I epsilon. That's if you've got some energy E and momentum K coming in. And this is V of Q, the Fourier transform of V of R minus V of R. And then you sum up all these diagrams and you get the scattering amplitude, where the relationship between curly A and F is that curly A is equal to 4 pi over M times F. This is the scattering amplitude, non-relativistic scattering amplitude that we defined here. So you find that A is 4 pi over M, 1 over K cotangent delta plus minus I K. Yeah. Psi is a field that creates your particle or destroys your particle. So it's got second quantized, but unlike a quantum field theory, there are no antiparticles. Okay, and because there are no antiparticles, this set of diagrams is the whole story. There are no bubbles coming off. There are no cross diagrams at this. If you have a instantaneous potential, that this would be a relativistic correction. I mean, so you don't have any of those. This sum of diagrams equals solving the non-relativistic Schrodinger equation. Yes, this psi dagger psi, this is, I should also mention they're at the same time. It's an instantaneous interaction, just like we would write down in a non-relativistic Schrodinger equation. So this really means, yeah, I should write it out. Psi dagger at T and R1, psi at T and R1, E at R1 minus R2, psi dagger at TR2, psi at TR2. Have what?
Three-body interaction.
I'm missing what that is. The
Three-body
Three-body.
interaction kind of.
seagull?
Three body.
One, two,
Three-body. Yes. If you wanted to talk about the triton, you're going to have to start putting in three-body interactions and so on. Yes, absolutely. I'm sorry. I didn't even understand that because I don't want to go there in these lectures. Okay. But yeah, you're absolutely right. Three-body interaction, four-body. Keep going.
Hello. So in the denominator, the k code delta function, we can expand in power of even power of k, and from that we can find the pole. It can give the binding energy. But what is the physical interpretation of the imaginary part ik?
Right. So you want to know where the IK comes from?
Yeah. No.
Yeah.
No. No. Not that actually. I mean to say, what is the physically interpret this ik term?
Diepsilon in the
Yeah, yeah.
propagator?
No, in this ik, I times k.
This thing?
Yeah, this one.
Okay, so that's a very good question. This is, so in this expression, K is defined to be square root of 2me, sorry, me, which is twice little me, where little m is the reduced mass. Okay, and so this is non-analytic in E. Where do you get non-analytic terms in quantum field theory? They always come from your propagator being on shell and the I epsilon playing a role. This is a good rule to remember, that if you have a non-analytic term, it's because there was a propagator that was on shell somewhere. Where is that here? Well, these two propagators could have been on shell because these two particles could scatter into real on-shell particles that could travel for a very long time and then recombine and scatter again. And that on-shell behavior means that when you calculate this loop diagram, you're going to get a cut. And that cut is the square root of me that comes here. And it's required for unitarity. So just like you know that the cross section, that, you know, there are these rules, if you take the imaginary part of the amplitude, that has to be, you know, the optical theorem, that it has to be related to the cross section for forward scattering. That exactly comes from this cut here where you say these two particles could have been on shell, and therefore I could relate the imaginary part of this diagram to the tree level scattering diagram. Good question. Okay, so now that we've got that machinery set up, I'm going to come back to it. First, though, I'm going to just say, let's suppose we have a square well again. I'll have the same notation. The width is delta, and the depth is equal to alpha squared over m delta squared. And I can compute the wave function I get for psi inside the square well. I get that it's got to be a regular solution. So it's J0 of kappa r, and sorry, where kappa is, as before, the square root of k squared plus alpha squared over delta squared. And outside, you find it's a linear combination that we wrote down, which is cos delta J0 of kr plus minus sine delta N0 of KR, and you do your matching of psi and psi prime at the boundary, and you get this final result that you can check on Mathematica if you want. It's the nasty expression. K outside, and then K sine kappa delta plus kappa cotangent K delta times cosine kappa delta over K cotangent A delta sine kappa delta minus kappa cosine kappa delta. And what we can do then is we can expand this and find the scattering length, and we find that this is equal to 1 over delta times tangent alpha over alpha minus 1 inverse plus order k squared. And this is minus 1 over scattering length. And this would be 1/2 r naught k squared if I computed it, and so on. So then you can plot this scattering length. And you find then that A over delta, and you find then it versus, sorry, not K, versus alpha, and it diverges at alpha is equal to an odd number of pi halves. So so on. Now, these divergences have an excellent physical meaning, because if delta, if we find then that if A is over delta is very, very big, namely it's near one of these dotted lines, then if you look at this expression for the amplitude, if you go to low enough k, all you have to worry about is this leading term, and you find a pole at k is equal to I over A. Now, since I took A to be very, very large, I can trust this result because k is very, very small in magnitude, which justifies the Taylor expansion. So this is self-consistent. This pole is reliable when k is small, or A is large, yeah.
Well, minus sign.
Oh yeah, so I got a minus sign one here, sorry.
No, it's, yeah.
Right. So remember that our outgoing plane wave looked like e to the IKR. If you're dominated by k equals imaginary I over A, what we find then is that for A bigger than 0, this is good, this falls off, exponential decay. And what we found is a solution, we have a bound state solution. And because I'm looking at the case of a very large A and k is small magnitude, that means a weak bound state solution. The large positive A corresponds to a very weakly bound state. Now, large negative A also corresponds to a pole in the amplitude, but it's exponentially growing. It's not a physical state in a Hilbert space. So it's called a virtual state. And its interpretation is that if you're sitting here, very large negative A, a small change in alpha would take you to a very large positive A, which is a weakly bound state. So by cranking up the potential to be slightly stronger, you suddenly get a weakly bound state. So a virtual state is an almost bound state. That's the way to think of it. Yes.
Plot the cross sections or something. For the virtual state, we'll see an enhancement just like a bound state.
I'm sorry.
So for the experiments, will we see an enhancement in the cross section for the virtual state?
You see an enhancement in an experiment.
Yeah, so what you see when you right, so we said that the differential cross section went like f squared. Since the differential cross section goes like f squared and f has a pole at k equals I times a 1 over a. Now, of course, the experimentalist isn't probing imaginary k, but when it's on the real axis near where the pole is, and if the pole's slightly off the real axis, you're going to get a big jump in f.
There is no way to like differentiate just using the experimental information that whether this enhancement is corresponding to a true bound state or a virtual state.
Oh, there is, because of the sign of A, because if you plot the phase shift, well, we're going to see that in the 1s0 for nucleon scattering in the 1s0 channel, you find a phase shift that looks like that. And so the behavior here tells you that A is large in magnitude because it's steep, and it is less than 0 because it's going up. Okay, and so this tells you that in the 1s0 channel, there's almost a bound state. In particular, for example, the neutron-neutron is almost bound. It's a good thing it's not, because if it was bound, there'd be no hydrogen in the universe, and there'd be no water, and there'd be no us. Yes.
But just from the neutron-neutron cross section, you can't tell if A is positive or negative.
I haven't looked at the cross section itself. I've only looked at the partial.
Because it's squared, just because it's squared. So you need some additional piece of information to decide that.
Oh, for the neutron-neutron, right. Well, I could have said neutron-proton. It's got it, looks similar.
Yeah, so there you have coherent scattering that gives you the sign, right? So you need some piece, but I think Rick is right that if you just had the cross section, you couldn't tell if it goes up or down at the end, right? If it goes to phase shift goes to 0 or 180, if you just had the cross section.
I'm sure you'll tell us.
I can do, yes.
And then if you look at the 3s0 phase shift, where there is a bound state, this has the deuteron, which is weakly bound in this channel, you find the cross section starts up and goes down. This is your delta. I mean. And so this behavior here tells you that you've got a large positive scattering length, and you expect that because you know there's a deuteron in that channel. Is this where you want me to stop, or? I've been talking for an hour. Did you want me to stop? Okay, we'll take a break here. Or maybe come talk to me one-on-one.
Hello. Sir, you mentioned that this enhancement, when A is large in the scattering amplitude or the phase shift. So is this the same thing happening for the multi-channel case, like the, in one word, can we say the Wigner curves actually the same thing, or it's a different kind of things?
I'm sorry, we'll have to talk one-on-one in the
Oh,
hearings. Just
yeah,
to-
yeah.
Why don't you come down, we'll talk during the break.